hear a materials chemistry talk, and you'll have a couple of slides that are synthesis, and the faculty would say, well, believe me, it's hard work, and move on to the next slide. So what you get to hear today is what's behind that hard work and blood and tears that come to making a molecule. Sravan came to UMASS in 2006. He joined the group of 2007 after doing an undergraduate degree, getting a good degree from Osmani University in India, had his master's from the NC of Pune, and went on to do a brief fellowship at the Institute of Technology, Kanpur, which Chandrasekhar was an alumnus of the department. He came to UMass to do synthesis, and if you are an organic chemist, you go into synthesis, and typically the end game is biology, something that can be injected somewhere to kill something. And the only thing we kill in our lab are the flies that come from the LGR events. So Sravan joined our lab, and I guess realized the fact that materials chemistry synthesis is actually as complicated as tough as natural synthesis. And for the first 2 years, we worked on a different project on proton transport. But then the third year, I asked him, to look into this problem of making triaramines because we got funding for this with collaborative with my client. And so the one thing that probably Sravan would appreciate throughout all the project is I actually tend to somehow give him hard molecules to synthesize. And he takes it with great gusto and with spirit and actually tries to conquer it very easily. Or at least not from my perspective. I guess you get the other story. And so Sravan also is an accomplished artist, a percussionist, a photographer, and a half-on hiker. You can climb up, but will not come down. So with that, come.
Thank you, DV, for the kind introduction. I would first like to thank the Research Trust Committee for giving me an opportunity to share my research. My research in the DV group primarily involves the synthesis of chiral-bridge triaramines. So, bridge triaramines belong to a class of heterohelicines. In order to know first what are heterohelicines, you need to know first what are helicines. Helicines, as the name suggests, are 5 conjugated molecules which have a helical backbone. As shown here, since there are 6 rings in this backbone, it's called a 6-helic. And since all the atoms in this molecule are carbons, it's called a carbohelicine. Bridge triaramines are also helical molecules but have a nitrogen atom in the center. Therefore, belong to a class of heterohelicines. Now, depending on the number of rings in the backbone, you can have a variety of bridge triaramines. As shown here, you can see from 5 rings all the way up to 7 rings. These molecules show axial chirality. That is, they are chiral due to the presence of an axis rather than a tetrahedral carbon surrounded by 4 different groups. Now, from our organic chemistry, we know for point chirality, the nomenclature used is RN. To differentiate point chirality from axial chirality, the nomenclature used is P and M. So if you have this molecule, and this portion of the molecule is shown in bold, is coming towards you, and the portion of the molecule not shown in bold is going away from you. And similarly, if this portion is coming towards you and this portion going away from you, you have either a right-handed helix or a left-handed helix. The right-handed helix is called the P, the left-handed helix is called the M. From the standpoint of applications, these molecules find use in polarized luminescence, display devices, optical storage devices, and nonlinear optics. Previously in the DV group, chiral-bridge triaramines, where R is a campionate, have been synthesized to study the polarized luminescence from these molecules. Professor Mike Barnes, who is an expert in single molecule spectroscopy in our department, studied the chiral-optical response of single helicine molecules on the surface to understand the interaction of light with chiral molecules. Now, the reason this result was so exciting is because for the first time it was shown that you could measure the chiral-optical response of a single molecule. More importantly, for the first time, you could decouple extrinsic factors such as solvent and environment from intrinsic factors such as orientation of the molecule on chiral-optical response. Since then, both our groups have been interested to see if we can enhance this chiral-optical response and further understand the role of extrinsic and intrinsic factors. So in order to do that, we need to first synthesize molecules based on this helicine. And to synthesize molecules based on this helicine, we need to first functionalize this thing. And the position which we chose for functionalization is this position, which I call the apical position, because when you build molecules starting from this structure, you're not going to compromise the symmetry of the building block. So today the story I'm going to tell you is about what were the challenges I faced in order to synthesize apically functionalized chiral bridge triangulomines and how we overcame those challenges. When Dee first talked to me about this project, I had almost worked by then 3 years on proton transport, and he said it will take me a week or two. I said, great, let's do it. Because I spent 3 years on one project. So, if you take a look at the structure of this molecule, if you want to say halogenated, there are 3 positions where the chemistry can happen. All the 3 positions being para to the nitrogen. So post-functionalization to obtain selective apical functionalization is not the value picture. So our approach or our strategy was, let's go from a bottom-up approach where we install the apical functionality on the parent apical ring before we form the helicity. This then makes the choice of the apical functionality very important because once it's chosen, it should survive the synthesis by making this helicity. So the first apical functionality which we chose was the TMSS scheme. It could be either TPTMSS scheme. The reason being, it's easy to install this molecule. And once installed, it will allow us to do Sonogashira reactions starting from this material, which are mild metal-mediated cross-coupling reactions. So here is first the synthesis of the apically functionalized TMS helicene. Campsonate can be installed by cleaving this allyl ether followed by an esterification reaction. The helicene can be formed by an intramolecular cyclization of this acid groups onto the phenyl rings. This molecule can be made by an amine CBr coupling. The ester or the TMS can be installed from an iodo-bromo ester. The ester can be made from the commercially available 2,6-dimethyl amine. Now the reason DV said it will take a week or two for this project is not because DV just wanted me to get this done scheme in 2 weeks. The reason being, even though the scheme has not been done in our lab or has not been reported in the literature, the chemistry involved in the scheme is very well established. So according to him, this scheme should take maximum 2 weeks, if I work hard. So here is first the synthesis of the TMSS scheme diester bromine. We start off with 2,6-dimethylamine, do an iodination at the 4th position to install the iron in the presence of iodine and pyridine, convert the NH2 to a bromine by a Sandmeyer reaction. Oxidize the methyl group in the presence of potassium permanganate to give the acid. The acid is then converted to ester in the presence of methanol and sulfuric acid to install the methyl groups. Now in palladium chemistry, it's very well known that oxidative coupling across a Ci bond is much faster than a CBr bond. So if you want to regioselectively couple TMS ethylene to this Ci position, the knob you can tune is the temperature of the reaction. So this reaction was done at 0 degrees temperature. And we get 93% yield of this compound where TMS regioselectively couples at the Ci bond. And this is confirmed by mass spectrometry, which shows the presence of bromine and the absence of iodine. So once we had the ester, our next step was to couple this diphenylamine to this bromine to form this molecule. Previously in the group, it was shown that palladium chemistry does not result in the product or does not result in the coupling of the diphenylamine to this Br bond, which is basically the Hartwig-Bucquoy coupling. So keeping that in mind, my strategy was to use Ullmann coupling, which is copper-based coupling, to couple this diphenylamine to the Cbr bond. So I take the 2 reactants, put in the catalyst, do the reaction for 65 hours at 150 degrees centigrade. I take the TLC, I see there's no change. I see the starting material. So our first guess for the failure of the reaction was there is probably a coordination of copper to this ethylene moiety, thereby preventing the reaction at this time. In order to see if that was true, we did a control reaction where we keep everything constant except convert this TMS group to a T-methyl group. And indeed the reaction proceeds with 85% yield. So here is where our 2-week process starts to fall apart. Because the apical functionality which we have chosen itself is preventing the formation of the helicity. So now we have to change the apical functionality and install a different apical functionality so that we can make chose was the bromine at the acyl position. Now there are two possible ways to get to this molecule. And remember, both ways require us to use copper because palladium does not work for the chemistry. So you can either have a bromoiodoester and couple the diphenylamine to this iodide, or have a dibromoester and couple this diphenylamine to this bromine to give this product. I mean, after a couple of steps, this product. So in palladium, it's universally known Ci oxidative coupling is faster than CPR. That is not universally known for copper. And moreover, the temperature knob which you have for palladium is not there for copper because Ullmann coupling itself is at 150 degrees centigrade. So it's very difficult to regioselectively couple this to this position if you have a bromoiodo or a bromo-bromo. So the reason we went for bromo-bromo is because previous experience in our lab with diesters with an iodo on a phenyl ring showed they have a very less shelf life. So it's very difficult to handle these esters. So we started to go with this method where we have a di-bromo ester. So here is first the synthesis of the di-bromo ester. We start off with the commercially available 4-bromo 2,6-dimethyl NH. Do a Sandwich reaction to convert the NH2 to a bromine, oxidize the methyl groups in the presence of KMnO4 to give the diacid. We were able to get a single crystal of the diacid in ethanol and water mixture. And here is the structure where you can see the two bromines shown in orange and the acid groups shown in red. The acid is then converted to an ester in the presence of methanol and sulfuric acid to install the methyl groups in 90%. Now we have the dibromo ester. Our next step was to make the diphenylamine from a Hartwig-Buchwald coupling where you have an iodobenzene, 2-amino-anisole in the presence of palladium GBA and DPPF as a catalyst to give the diphenylamine. So now we have both the parts of the molecule to form this molecule. Now we have to couple them to give this molecule. Now we were taking a big bet here. Now the coupling can happen either here or here. But it was okay for us, even if some amount of the coupling happened here, to give this compound, and we can use this compound, whatever little amount we have, to go ahead and make the hexene. So if you take a look at this ester, this CPR bond is a sterically unhindered bond and electronically unactivated bond. This CBR bond is a sterically hindered bond because of two ortho functionalities adjacent to it, and electronically activated because of two orthoester functionalities. To give you a better picture, here is the space-filled model of this compound. You can clearly see how unhindered this bromine is with respect to this bromine. Right? So, as I said, palladium does not work. So, our goal is to regionally selectively couple copper using copper, this diphenylamine, to this CBR bond. There is a very little and very old literature on an effect called the orthocarboxylate effect. This was published in '85 by a Xerox company in Canada. So what it says is if you have an orthocarboxylic acid adjacent to a bromine atom, and in the presence of a copper bond, it forms a chelate which results in rapid dehallucination. Our hope was if somehow this copper could be directed to this CBR bond due to the presence of this ester, we could achieve regioselective coupling of this diester to the diphenylamine. Now when we do this reaction, there are three possibilities. You can either have coupling at both the positions, since the temperature